Hey, what's going on, guys? Let's do this problem right here. This question is asking to find out heat transfer rate when we have copper and the heat transfer rate when we have aluminium. Now let's see how we can find out Q dot. So whenever we have conduction question, to find the heat transfer rate, we always use this equation, that is Q dot is equivalent to Ka delta T over L, right? This equation is actually negative, but you know that delta T is equivalent to T2 minus T1, right? So this equation can be positive when you take this one opposite, like delta T is equal to T1 minus T2. You can make this equation positive. So here, that's what we are going to do. So initially is always going to be the hot temperature, and finally is always going to be the cold temperature. So this is going to be 100. So instead of saying hot cold, we can say higher temperature is always initial and lower temperature is always the final, right? So this is going to be 100 minus 0, and that's going to be 100. And if we use T1 minus T2, we shouldn't write this negative right here. So this is going to be just Ka delta T. Now let's go ahead and plug the values. K is thermal conductivity, A is cross-sectional area, that's given, and length is also given, length of this pipe, right? And delta T we found out right here, that's 100 degrees Celsius. Now let's find out the heat transfer rate for copper. So Q dot Cu. So Q dot Cu, we have to use the thermal conductivity for copper, that's provided right here. That's 385, right? 385, and this is in watts per meter Kelvin. And then we have area, that is 0.01 meter square, 0.001 meter square, and delta T is 100 degrees Celsius. Now here the thing is, temperature change in degrees Celsius and Kelvin is going to be same thing, because even if you add 273 to both value and subtract this one, you're gonna get the same value. So you can put 100 Kelvin or 100 degrees Celsius. In this case, 100 Kelvin is better, because when we have watts per meter Kelvin, if we put 100 Kelvin, these two will cancel each other and we will get the final unit correct, right? Final unit we expect watts, because Q dot is heat transfer rate. So we know that heat transfer is in joule, and if it's rate, joules per second, that should be watts. Now in the bottom we are going to have length, that is 1.2 meter, and from this one you can notice that this meter square, so one of the meter cancels here and one of the meter cancels with this bottom, and Kelvin cancels. Finally you will end up with watts. Now let's calculate this value, and if you plug all these value in calculator, you should get 32.08. This is approximately 32 watts, right? So this is when we have copper. Now let's see what happens when we have aluminum bar, right? So when we have aluminum bar, the only thing that's going to change is this value, the K value, that is thermal conductivity. Now let's plug all the values. So here we are going to have Q dot Al is equivalent to 205 watts per meter Kelvin times the same area, that is 0.001 meter square, times the temperature difference also going to be the same, that's 100 Kelvin, and then in the denominator we are going to have the length, that is 1.2 meter, and if you calculate this value you should get 17 watts. And that's how we do this kind of problems. I hope you guys find this video helpful. See you next time.